Hi to everyone. This is the activity for the lab number 5, the binomial distribution. All right, so here in the activity that is posted on Blackboard, you have information about the binomial distribution. Essentially, it's this is explaining the corresponding video or the video lecture for binomial, but it's a distribution that gives you the probability for certain number of successes when you perform an experiment that results only in success or failure or no success, and you repeat the experiment a finite amount of times. How do you know the probability? For example, when you toss a coin 5 times, if you have a fair coin, what is the probability that you can observe 4 heads, 3 heads, 2 heads? Yeah, those responses are given by the binomial distribution. All right, so here we have to read something. Calculating probabilities. The probability mass function gives the probability when the random variable x equal to a certain number. All right, again, you can see the video for the binomial. But here, this part is going to be important. When using hypothesis testing, we're going to use a 95% cutoff value to determine if the observed value of k is rare enough low probability to suggest a treatment effect. All of this hypothesis testing is going to be covered later in the course with more detail, but I would try to explain what we're doing here with the binomial right now. All right, so let's start with the activity. Generic binomial 1. From the lecture notes, we calculated the probability distribution function and the cumulative probability function for a binomial distribution with n equal to 4 trials and p equal to 0.10. Use Minitab to find both to verify they are the same. All right, the first part is in C1, type in all the possible values of k successes. 1 per cell, 0, 1, 2, 3, 4. So we are going to simulate a binomial distribution when we have 4 trials. 4 trials, the maximum amount of successes we can observe are 4. So that's why we have to put here in the column number 1, 0 successes, 1 success, 2 successes, 3, and 4. Always when you have a binomial, you need 2 values, the number of trials, number of times you are repeating the experiment, and the probability of success in only 1 trial. In this case, it's going to be 0.10. But the end, the number of trials is 4. So we have 4 trials. How many successes can we observe? At most, 4. So we have this. Now from the menu, go to the menu, calc probability distributions binomial. So we go calc probability distributions. Notice here in this version for Mac or this web app, we don't have directly the option for binomials. So we have to click on probability distributions and then probability density function. Click there, and then we have to choose here where it says distribution. In this part here, you have to click here and choose the binomial. Binomial, see? It's some of the first one. Binomial number of trials, in this case, is 4. Event probability again is the probability of success in only 1 trial, is given by 0.10 in this case. So write 0.10. From form of input, a single value, no, I want a column of values. Values are stored in the column C1. So double click C1. Display a table of probability density values. You can display a table or you can put it in into a column. I'm going to choose display the table separately. So after all of this, you click OK. And there you have, you see? When you repeat an experiment that can result only in success or failure with probability of success of 0.10, you repeat the experiment 4 times, what is the probability you observe 0 successes? 0.6561, 1 success, 0.2916, 2, 0.0486, and so on. This is the interpretation for this. So this is the first pass. This is the probability mass function part. This one is this one here. Now, cumulative distribution function. We're going to do the same we did before. Go to Calc, probability distributions, but now choose cumulative distribution function. And then everything is the same. Form of input, choose column of values. The values are stored in the column C1, or they are coming from C1. Distribution, choose binomial. Number of trials, we are still with the same problem. So n is equal to 4, and the probability is 0.10. Display the table of cumulative probabilities, the same. So you see it's exactly the same as before, but we only shows cumulative probability. So then click OK. And there you have. We have another table. This table, what is the difference between this table and the other one? For the other one, we had the probabilities for exactly 0 successes, exactly 1, exactly 2. This table gives you the probability for less or equal successes. For example, what is the probability we observe 0 or less successes? Since we cannot have a negative number, the probability for the cumulative, in this case is for 0, is going to be the same as the probability for exact 0. You can compare that. 0.6561, 0.6561, you see? But notice that these probabilities are going to change for other numbers. For 1, the probability is 0.9477. What is this? What is the probability we observe 1 or 0? 2, 0.9963. What is this? The probability we observe 2, 1, or 0. For x equal to 3.9999 is the probability we observe 0, 1, 2, or 3. So these are cumulative probability, less or equal than the given number. And in the previous case, they were exact. Exactly 0, exactly 1, exactly 2, exactly 3. All right. And then this question, at how many successes in the sample can we reasonably assume a treatment effect? All right. That's why I mentioned at the beginning, we have to consider this when using hypothesis testing. We're going to use a 95% cutoff value to determine if the observed value of K is the rare enough to suggest a treatment. What do we have to do here? You have to go to the cumulative distribution, and essentially try to identify the number of successes such that the cumulative is greater than 0.95. Notice the cumulative for 0 is 0.6561. The cumulative for 1 is 0.9477. We haven't reached yet the 0.95. So the number 2 is, I know, is more than 0.95, but this is the best we can do right now because we don't have a value exactly for 0.95. So in this case, we can say that to respond to this question, we could observe a treatment effect at x equal to after 2 successes. After 2 successes. Now, generic binomial number 2, given the same probability of the success, p equal to 0.10, calculate the PMF and the CDF, the sample size is increased to 12. So we're going to repeat the same, but now the number is going to be increased to 12. So you have to type here 0, 1, 2, 3, 4, and up to 12. I'm going to do it in the column number 2. Remember, you don't have to, you can enter each value for each cell. That's okay, but I recommend to take advantage of the commands given here. For example, here, calc, go in the menu, go to calc, make pattern data, simple set of numbers, store pattern data in the column C2 from the first value 1 up to 12. And if you need something more than 12, you can do it as well. In steps of 1, number of times solution value 1 and 1, so okay. So after that, notice in the column number 2, we have the numbers from 1 up to 12. Now repeat the process. Go to calc, probability distributions. First, the PMF, probability density function, form of input. You have to select column values. From, we have the information now in the column C2, so double click C2. Binomial, here be careful. Here now we're using 12 trials. 12 trials. So that's why we have to put here 12. The probability is the same, 0.10. Binomial 12.10, column value, so I think it's everything correct. So I click OK. And there you have. You're going to have the probabilities for 1 success, 2, 3, 4, 5, 6, 7. All right, when we repeat the same experiment 12 times. And for the cumulative, do the same. Go to calc, probability distributions, cumulative in this case, a column of values. They are stored in C2, double click. Binomial, remember to change this to 12.10. Display a table of cumulative probabilities. Okay. And there you have. So what is the probability we observe? Less or equal than 2, 0.88913. Less or equal than 3, 0.97436. And then you have to introduce these values for the PMF. I mean, here you have to type 0, 1, 2, 3, 4, and so on until up to 12. For the PMF, you're going to write here, for example, for the first one, 0.376573 for 0, for 1. Oh, I'm sorry. I did a mistake. I'm sorry. Let me fix that. Notice, I started with the number 1. What happened with the 0? I should have included. I'm sorry. I can fix this quick. I'm going to delete this. The last two for density and cumulative. And I'm going to choose again calc, make parent data, simple set of numbers. I'm sorry, this is my mistake. Store the data in C2 the same, but you have to start from 0 because zeros must be taken into account also. 0, 1, and then OK. And notice, now I have included the 0. Yeah, I'm sorry, I did a mistake. So 0, now repeat the process before, calc, probability distributions for the PMF, probability density function, column value C2, number 12 is 12. So everything is the same. Just click again OK. And now you have the 0, see? Yeah, I'm sorry, it was my mistake. For the cumulative, the same, calc, probability distributions, choose cumulative. Everything is as we had it before, column value C2, binomial 12.10. So click OK. but now we have the cumulative for 0. So here, I'm sorry, for 0, 1, 2, 3, 4, for 0, the probability, the PMF, is 0.02824. 282430 0.37 6573 and so on, right? With the probability distribution, you complete this PMF for all the values from 0 up to 12. So please fill these values here. And what about the CDF? For the CDF, you have to use the cumulative distribution function. For the CDF, the value is the same as the PMF, 0.28243 for 1.65900 and so on. You will have to complete, you will have to write all these values here. All right, so let's continue. Now the same question, at how many successes in the sample can we reasonably assume a treatment effect? So again, do the cumulative for this. Where do we have something, the first cumulative value greater than 0.95? Notice for number 2 we have 0.88. Then from 3 we have 0.97. This is greater than 0.95. So will be from 3 after 3 successes. There you have. Now, egg problem. It says Larry heard that one out of 4 eggs has salmonella. Because of this, he only ever cooks 3 eggs at a time. This follows a binomial distribution. Describe how the conditions are met and the parameters. All right, the conditions are met because we have when we consider to cook only 1 egg, yeah, we have only 2 outcomes. It can have salmonella or it doesn't have salmonella. So in this case, the success, yeah, it's weird. The success is that it has salmonella. And the probability is 1 out of 4. Yeah, because it says 1 out of 4. And this guy is going to repeat the experiment 3 times. You see that? So you write here n equal to 3. And P is equal to 1 out of 4, or 1 divided by 4 is 0.25. And then you have to repeat the same as we did at the Minitab. I'm going to do it here quick. You can store the values in the column. I'm going to store the values in C3. Notice, in this case, n is equal to 3. So what are the possible numbers? 0, 1, 2, and 3. We cannot have more than 3, right? If we are repeating the experiment, or we are cooking only 3 eggs, how can we have more than 3 eggs with salmonella? It's impossible. That's why from 0 up to 3. Then repeat the process. Calc probability distributions, probability density function, binomial. Be careful here. Now the values are stored. They're coming from C3. Binomial, how many trials? N is equal to 3. And change the probability, 0.25. 0.25. Display the table. OK. And there you have. Probability we observe. We have 1 egg with salmonella, 0.42. 0 eggs with salmonella, 0.42. 1.42 was the same, right? And 2 eggs, 0.14, and so on. Now the cumulative, calc, probability distributions. cumulative, the same. Oh, no, not the same, right? Type n equal to 3.25. Values coming from C3. It seems to be correct, and then OK. Probability we observe 0x with Salmonella, 0.42. Probability we observe 1x out of 3 with Salmonella, 0.84, and so on. So you have to complete these values in the table. 0, 1, 2, and 3. And then the PMF, just these values. And for the cumulative, use these values. All right. Questions. What is the probability that 0 of the 3x will have Salmonella? Go to the probability density function, the PMF. Exactly 0.42. 0.42, 1875. There you have. What is the probability that there are at most 2 eggs that have Salmonella? At most 2 means a maximum of 2. So that means all the numbers from 2 and below. So in this case, you can add all the values from 0, 1, and 2, or you can use simply the value for 2 in the cumulative. So in this case, at most 2 means 0, 1, or 2, or no more than 2, or x no more than 2. So in this case, only use this value, 0.98, 438. 0.98, 438. And there you have. Now, birth control shot problem. The birth control shot is a very effective method of birth control. In typical use, approximately 3% of women who use the shot become pregnant. Approximately 3% of women who use the shot become pregnant. Oh, well, we choose 20 women who have the shot and count the number who become pregnant in the following year. Use Minitab to calculate the PMF and CADF of the distribution and answer the question. Explain what is a binomial distribution, all right? Yeah, this can be modeled with a binomial distribution. Why? We need to have one experiment that results in only success or failure. In this case, the success is getting pregnant. Yeah, I know from a certain point of view it can be success or not, but here is a success. The success is to become pregnant for the woman. So the probability of success is 3%. And we are repeating the experiment many times because we are taking into account 20 women. So in this case, yes, it is. And we choose n equal to 20. And probability of success, or getting pregnant in this case, is 3%. Be careful, it's 3%. But with decimals, remember when you have this in percentage, you have to, if you want to express this in decimal, you need without the similar percentage, you need to divide this by 100. So it's going to be 0.03. We have a number distribution with these parameters. There you have. Explain, well, there you have the parameters, and then you have to create the table. So here I'm going to store the values from in C4. Remember, if n is 20, so we have 0, 1, 2, 3, 4, 5. So you can use again this calc make parent data, simple set of numbers, 0 up to 20. Store the values in C4. 0, 20, 1. There you have. So now you see, now the values are stored in C4 from 0 up to 20. And now repeat the process that we have done before. Go to calc, probability distribution, the first one, the probability density function, binomial, from the column C4, number of trials, here is going to be n equal to 20, and p equal to 0.03. Again, be careful with that. 3% of success in decimals is 0.03. Only divide 3 by 100 and remove the symbol, the percentage. So I think everything is okay. Display the table. And there you have, you see, all the values. Probability we see 0 women pregnant, 0.5. Probability we see one woman pregnant, 0.33, 2 out of the 20, 0.09, and so on. See that? Now for the cumulative, do the same. We'll do calc, probability distribution, cumulative, account the column values, they come from C4, binomial, n equal to 20, 0.03, and display. Okay, there you have. You see? Now respond to these questions. What is the probability exactly one woman becomes pregnant? Exactly one. Go to the probability density function of the PMF. Exactly one is 0.336368. This one here. 0.336368. 0.336368. What is the probability that at most one of the women become pregnant with typical use? At most one means one, no more than one. So that means 0, 1. You can add these two values, or you can look directly at the cumulative. The cumulative for 1 is 0.88016. 0.88016. What is the probability that at least one of the women becomes pregnant with typical use? At least one means one or more. At least one means 1 or 2 or 3 or 4 or 5 or 6 or 7 and so on until what? How many tries we have? Well, I mean, how many women we have? So we have 20. So will be, you will have to add all the probabilities from 1 up to 20. Yeah? But I'm going to give you one hint to compute this in a simpler way. Only subtract from 1 the probability of 0, because that's going to be the complement. So if you do this, subtract 1 minus the probability of 0, is 1 minus 0.54379. I got 0.4561. 1 minus 0.54379. I got 0.45621. There you have. Again, why I subtracted from 1? Because we can say that the whole sample space is that all of them, all the possibilities are from 0 up to 20, but I want only 1 or more, so subtract the sum of these probabilities. I mean, for the density, for the PMFs is going to be 1, so you want only from 1 or more, subtract 1 minus the probability of 0. And this is the desired probability. And then after how many pregnancies could we claim that the shot is not 3% effective? So here you will have to look at the cumulative and see from what success the difference is less than 3%. Notice from 0.54 to 0.88 obviously is more than 0.03. From 0.88 to 0.97 is more than 0.03. From 0.97 to 0.99, from here up to here, notice, subtract this 0.99, 733 minus 0.97, 899 is 0.18 approximately. So from after how many pregnancies could we claim the shot is not 3% effective? After one pregnancy. Yeah? After one. No, I'm sorry. After two. I mean, from the third one and onward, is the probability efficiency is going to be more than 3. I mean, less than 3%. So it's going to be after 2. And now finally, these concept questions, which of the following is the PDF and the CDF? So I think you can respond this by yourselves, all right? Only pay attention to what we obtained before and what I explained at the beginning. What is the PDF and what is the CDF, and how do you know that? All right, that's all by now. See you in the next activity.